Hi, so I'll be talking about the Ford-Fulkerson algorithm. The Ford-Fulkerson algorithm is based off of three main constructs, mainly in graph theory. One construct is the residual network, and the next one is augmenting paths of the residual network. And finally, we have cuts, which is similar to the minimum spanning tree argument. For the residual network, as you can see, given a graph G, we have a residual network GF. It tells us how many units of flow we can add. So intuitively speaking, as you can see on this side, we have a graph here where each black line is the capacity of the edge, and this is the amount of, say, flow we can pass through on this edge. And here we have, for example, 2 out of 3 flow for this path that we can get through. And this may be the optimal, um, this may be the optimal flow for the entire graph from S to T, but we do not know. Thus, we have to use max flow, and Ford-Fulkerson is one of the main principles or algorithms that is used to solve max flow main cut. And one thing that we should note is that here on the slides, we have that CF, which is capacity of the residual network between any node U and V, is equal to the total capacity of U and V in the original graph, as you can see here, 3, for example, minus the flow of U and V. So as you can see here, we have 2 is the flow. So what would be the residual capacity here? The residual capacity would be 1. And formally speaking, the edge between U and V, if there is no edge, that means that there is no flow or no capacity. So in the original graph here, we do not have an edge from, say, this node to this node because it does not have a flow. And in the residual network, if one of these paths, say 2 out of 2, flow is taken out of this capacity, then that means that there is no edge on the residual network between these two nodes. And the third argument is the ST cut. The ST cut of a flow net is a partition of V. V is the set of all vertices inside of our graph. V contains two disjoint sets, S and T. S, denoted by this capital S here, is all of the nodes from the starting set. And T here is all of the nodes in the source set, in the sink set. As you can see, we do not need to pick adjacent nodes to be in the S set. For the S set, it must contain the node S, and for the T set, it must contain the node T. And the total flow between the two cuts is the total capacity going in and out of the two cuts. So for example, we have here is 2 plus 2, therefore it's here, as you can see, S to A, S to B. And here we have now we go from T to S, therefore this is a reverse flow. For example, A to D is -2, as denoted by this -2 over here. As you can see here, D to B is a source to the destination. Therefore, we have one flow going in the positive direction. This is +1 here. D to C, as you can see here, the edge is reversed. We have C going to D, and that is from the destination to the source. Therefore, we have a negative flow, denoted by -1. And the total flow between all of this is 4. And, and the capacity of the flow cut is the total capacity of all the capacities in the original graph. So if we have any nodes going from S to T, for example, say this edge, we will add its capacity to the C of ST. So for example, here we have 3 going from S to A. So there's a very important theorem that we need to know about for max flow main cut. The idea is C of St. C of St is the total capacity from S to T. As you can see, this is the total amount of flow we can possibly give from one side to the other. And for example, say this 0 and this 0, we're giving the most optimistic estimates of the possible flow that can go through between these cuts. Because they are originally negative, we set them to 0 because we could just emit no flow through that edge. So we want to find the minimum cut because our C is the upper bound of the possible flow we can possibly send throughout the graph. Therefore, we are trying to find the minimum cut. The minimum cut, as you can see, is not this set. Now, if F is a maximum flow, then therefore there is some cut that is saturated. If there is no cut that is saturated, you can send one extra flow or more through from S to T. It's denoted as an augmenting path. Therefore, because we'll have sent all the augmenting paths, F will no longer emit any more augmenting paths. The pseudocode for this algorithm is very simple. It is, while there is an augmenting path F prime, you can add F prime to F, and then you can return F, which is the total set of flow going from S to T. It is for every edge, we will have a specific number, which is the flow amount that can be transferred for the optimal max flow result. Now, there are other applications of Ford-Fulkerson other than max flow. Before spoiling it, do not look on the left side. We can use the algorithm to compute things like the maximum edge disjoint paths of a graph from S to T. How would we go about it? Well, we can set the edge to capacity 1, and then we can run max flow. Why does this work? Because we want the maximum number of edge disjoint paths. For the maximum number of edge disjoint paths, we can treat each edge similarly, and thus we can treat each edge with capacity 1. If there are two paths P1 and P2 that share one edge, then they are not edge disjoint. Therefore, you can only allow that edge to be used in one path. That's why we have a maximum capacity of 1 for every edge, because no two paths can use the same edge. And because of the integrality of flow, you are only allowed integer values. Therefore, if the capacity is 1, then therefore you can only have 0 or 1 for your flow through that edge. 1 means that you have taken the edge, and 0 means that you did not decide to select that edge to be one of the edge disjoint paths from S to T. Now, we can use the algorithm to compute the maximum vertex disjoint paths as well. This one is not immediately obvious. Think about it for a minute. Now, the solution is we can turn each node into two nodes with a single edge of capacity 1 connecting both of them. This means that we can run max flow and treat each node as a specific edge. We do not care about the other edges because we're not caring about the edge disjoint paths. Therefore, we can send all other edges with infinite capacity. Now the bottleneck will be at the nodes with the edge capacities of 1. Then you can run max flow again. If two paths use a specific vertex in the original graph, then we cannot possibly have a max flow with surpassing the capacity of 1 in our single edge. Therefore, we can guarantee that every node inside of our graph, after running max flow on this augmented graph, will be only used once or none. Now, we can also use the algorithm to compute heterosexual Tinder. I say heterosexual because it must be clearly bipartite, aka male and female on each side of the graph. Now, all guys can be on one side, either the right side or the left side of the bipartite graph, but for this example, we'll say that the guys are on the left side and the girls are on the right side. If a guy likes a girl and a girl likes a guy, then they are mutually attracted. Therefore, we can have an edge between them to connect them. Now, we want to have the most amount of people matched in Tinder. Therefore, we should put all guys on one side, all girls on the other. But for the ones that connect, we have a capacity of 1 for the edges in between. Also, a single guy can only match with a single girl. We cannot allow the guy to match with multiple girls because they must be paired with each other in the end. Therefore, we only send one flow to each individual male. We'll send this through the original S node that will contain all of the capacity. And then we will connect all the female to the sync node with capacity 1 as well, because each female can only match with one guy. And then we can run max flow. Running max flow will give us the most amount of matches possible between all the guys and all the girls given their preferences.